All right, this whole chapter, we've been doing different things with polynomials. We've been especially graphing them. We've been factoring them. We've been finding the zeros, looking at like the degree, how to name them, lots of different things with polynomials. Today, we're going to get real into the specifics of finding the zeros of a polynomial. And sometimes it's really easy. Like sometimes if we have a cubic graph that crosses it 3 times, then we can find those zeros pretty straightforward. We can use our calculator to help us out. But there's going to be some times where the calculator doesn't give us all the zeros. Maybe sometimes some of the zeros are imaginary, or sometimes they're irrational, like they're radicals and they're decimals. And so they're not quite as easy to pull out and decide what we got. So we're going to find out ways that we can algebraically kind of figure out what are our zeros going to be. So there's 2 different statements that I'm going to give you to start with that will always hold true. If a complex number is a zero, then its conjugate is also a zero. We talked about the word conjugate a little bit last chapter, and I told you we were going to continue to run into those from time to time. And so what that means is if I have a zero of 3i, then negative 3i is also a zero, which is what we call the conjugate of 3i. Where we really saw conjugates is if I had like 2 plus 5i, bless you, then the conjugate of that would be 2 minus 5i. So what we do is we change the sign. Remember, this one here doesn't have a real part in front of it. So when we talk about a complex number, it has a real part and an imaginary part. So the real part here is assumed to be 0. So this is 0 plus 3i, 0 minus 3i. But we don't really need to write the 0. Here is where you actually see the real part and the imaginary part together. So basically what we're saying here is if you have an imaginary 0, you always have 2 of them. They always come in pairs. You're not just going to have one imaginary 0. You're always going to have 2 of them. Okay, the second statement that is very similar to that if an irrational number is a 0, then its conjugate is also a 0. So irrational numbers can also have conjugates. I'll give you a couple of examples of what that would look like. If I just said radical 5, and when we talk about an irrational number, it's a decimal that goes on forever. So the most common irrational number is pi, but we don't really see pi in algebra very often. So when we talk about an irrational number here, we're talking about like a radical that's not a perfect square. So if I take the square root of 5 in my calculator, I get this decimal that goes on and on and on and on. It doesn't repeat, it doesn't stop, and that's what makes it irrational. We can't write it as a fraction. And so the conjugate of that would be negative radical 5. Same as like an imaginary or a complex number. If I did 2 plus radical 7, then the conjugate of that would be 2 minus radical 7. And so those also come in pairs. If I have one irrational number, then I always have another, and it's the conjugate of the first one. And so those 2 things will always hold true. And where that helps us is if I know that I have one imaginary, I know it's got to have another one with it. Same thing for any irrational. And we're going to see that in a couple of examples that we do today. But just know that that will always hold true for any polynomial, no matter what type of polynomial we have. Okay, so if I give you an example here. If I have zeros of 1 and 3i, you're going to see a question like this. Find a polynomial of the least degree with these zeros. And here's where it's important to remember that rule that we just talked about, okay? Because they may not give me both of the imaginary zeros. So in this one, they only give me 3i. 3i is a 0. Because it's imaginary, then we would also have negative 3i. It wasn't given to me at the beginning, but we know it to be true based on what we just talked about. Last week, we talked a little bit about finding the factors and finding the zeros of a polynomial, and we said that those two correlate with each other pretty easily. So in this case, the zeros are 1, 3i, and negative 3i, and to write the factors, we always do x minus whatever the 0 is. So this would be x minus 1. And same thing for the imaginary zeros. X minus 3i, and then x plus 3i. But what we want to do here is we want to write this in standard form. We want to write this polynomial in standard form. Right now, this is what we call factored form, and so we got to do a little bit of multiplication to get it into standard form. When we do this, we always want to do the conjugates first. We don't want to multiply this by this, because trust me, it's going to get messy if you do it that way. Okay? You always want to do the two that are opposites of one another, or conjugates of one another. And that'll make things a little bit easier. Okay, I also will tell you this. Because we have conjugates, my answer will not have i's in the answer. Okay? When we multiply this together, we think, oh man, this is going to get messy because we have i's. But when I write my polynomial, it's going to look like just a normal old polynomial when we get done. If you have i's in your polynomial, then you've done something wrong. Okay? We're not going to do any polynomials where we have i's in our answer. So we're going to FOIL to start with. We're going to do x times x, x times 3i, negative 3i times x, negative 3i times 3i. Okay, and we did a lot of foiling with imaginaries when we did this way back when. This one's a little bit different because we have some x's attached, but because these two are conjugates of one another, then what should happen is those two middle terms should disappear. The 3ix's cancel each other out. And then once again, we see I squared. And we said way back when we talked about imaginaries, anytime I see I squared is really negative 1. And so then this would become x squared plus 9. And I haven't multiplied by x minus 1 yet, so I'm going to bring the x minus 1 down. And now I'm going to multiply the x minus 1, because I haven't used it yet, and multiply it by x squared plus 9. And so we just got to FOIL one more time. And when I do that, we get x cubed, x times x squared. I'm going to do it a little bit out of order. I'm going to do the inside part first. That way it's in standard form, minus x squared. And then I'm going to take x times 9. I know we usually do the outside and then the inside, but that way we don't have to rewrite it when we get done. And then negative 1 times 9 is negative 9. So here would be an example of a function or polynomial with degree 3. Okay. And we know it's degree 3 because we had 3 different zeros. Okay? And those would be my 3 zeros. Okay, I'm not going to take the time to graph this, but if I did graph this one, just to kind of show you what this would look like. And I don't know exactly what it looks like, but it's going to take on something similar to that. It's going to cross the x-axis at 1. It's never going to cross it again. And the fact that it never crosses it again tells me that my other two zeros are imaginary. Okay? And you could put that in your calculator and you could kind of verify that again as well. But just kind of, once again, trying to draw that connection there. That connection is a really big deal. Okay? Understanding how the zeros and the graph kind of correlate with one another and understanding how they work together is a really big part of what we're going to do today. Okay, this theorem here, we won't use this theorem a lot. What I will tell you is that, like when I took college algebra, we used this theorem all the time. I use this pretty heavily because we didn't rely as much on graphing calculators as we do now. Okay, and now that we have the technology to use and we have the ability to be able to do things a little bit easier, then graphing calculators have taken this theorem and we just don't use it as much. So that's a good thing and a bad thing, but there are still some times where the rational zero theorem can be used. But sometimes, and I'll kind of show you how and why it could be used, but sometimes it doesn't really help us a ton. And that's why we use graphing calculators more so than the actual rational zero theorem. So here's what the rational zero theorem looks like. We have a polynomial. The only two things that we are going to pay attention to here is the leading term and the constant. The leading term is the term at the very beginning, the one that has the highest degree. The constant is the number at the end that does not have a variable attached to it. I don't care about all the stuff in the middle. Okay, and that's why I just put some dots there, because we might have this big old long polynomial, but I don't care about all the stuff in the middle. All I care about is make sure it's in standard form first, and then pay attention to the first term and the last term, basically. Okay, this term here is what we call our p-value, and the leading coefficient is what we call our q-value. Okay, so p is going to represent factors of the constant, whatever that constant number is. Q is going to give me factors of, thank you, Mr. Frecking. Factors of the lead coefficient. Okay, the coefficient is the number out in front. Okay. So as we look at this, I'm going to give you an example. Of a polynomial. This is my p-value. This is my q-value. I don't care about this stuff in the middle. The 11 and the 10, we don't use that at all. All I care about is the last term is my p-value, the first is my q-value. Okay, but here's the part that we got to do a little bit of work with. Okay, so p is 4, but we're going to list out all the things, all the factors that go into 4. And sometimes, and that's where this could get really dicey, is let's say I have a number like 60 at the end. Then there would be a lot of things that go into 60, right? Well, 4, not too many things. 1, 2, and 4. That's it. Those are the 3 things that go into 4. Okay? As far as q, we do 1 and 3. And we're going to take all of our p-values and divide them by all of our q-values. So we're going to do P divided by Q. And what I try to do here is I try to organize it, and this could give me a really large list of things that could be possibilities, okay? So in this case here, I'm going to take all of the p-values and I'm going to start by dividing them by 1. I just try to organize it in some way. So if I divide 1, 2, and 4 all by 1, it's just going to give me the same thing back. But we always put plus or minus on each one. So I'm going to take 1, 2, and 4, I'm going to divide it by 1, and that gives me 1, 2, and 4 again, but we put plus or minus on all of them. And then I'm going to take 1, 2, and 4, and I'm going to divide it by 3. So 1 divided by 3, 2 divided by 3, or 4 divided by 3. The reason we call this the rational zero theorem these are the possible rational zeros of this polynomial. These are the things that could be zeros. Okay? Now, if I have a 4th degree polynomial, how many zeros could I possibly have? What's the most I could have? 4, right? Here, we got 1, 2, 3, 4, 5, 6 numbers, but they all have plus or minus on it, so we actually have 12 possibilities here. We can't use all 12 of those, right? And so, be thankful that you guys have graphing calculators, because here's what I had to do back in college algebra when I took this. Here's my 12 possibilities. I then had to use synthetic division, and we would try 1, and we would see if 1 worked. Is it a 0? Do I get a remainder of 0? Then I would try negative 1, and I would keep doing it until I found something that worked, okay? And we would have 12 possible things that we could check. And what happens if 2 of them are imaginary? Well, they don't even show up in the rational 0. Or if they're radicals, they don't show up in the rational 0 theorem. And so sometimes we might have imaginary or radical zeros that don't show up in that situation. So if I graph this one, this would cross the x-axis at 2/3, and it crosses it at -1. Okay, and I'm just going to save some time here because we got a lot of stuff I want to try to get through today. These are 2 places that it's going to cross. 2/3 is one of my possibilities. It's a positive 2/3. -1 is another one of my possibilities. So out of those 12 possibilities, only 2 of those 12 are actually rational zeros of that actual polynomial. The other 2 zeros are irrational because they are radicals. They're decimals that go on forever. So not all of those can work, and in fact, not very many of them are actually going to work. Okay, and so that would be a really time-consuming thing. Okay, so sometimes just be thankful that you guys live in the technology age, or at least a little bit down the road, where you can make things a little bit shorter. Okay? And I'm not going to force you to do that because we have technology to use. Why I'm not going to make you do that. And that's why we don't use this theorem quite as much as we used to. But it used to be a really big help to at least be able to start breaking down our polynomial. All right, so I'm going to give you a couple of these examples, and I want to show you some different possibilities of what could happen here. Okay, this first one that we're going to do, I'm going to give you a polynomial. Okay, and we're going to say -5 is a 0 of this polynomial. Sometimes they're going to give us one where it's going to ask us to find all the zeros. Nothing's going to be given to me. This one, it tells me that -5 is a 0. But we want to find the other zeros of this polynomial. Okay, and so here's kind of how we're going to go about this. This is where we're going to use what we did on Thursday. We talked about synthetic division. I'm going to put -5 into my box. Okay, it's not a factor, it's a 0, so we do not do the opposite here. Okay, if it's written as x plus 5, I would do the opposite, but here negative 5 is the actual number of the 0. My coefficients are 1, 5, negative 2, negative 10. Okay, so we're going to bring down, and before I go too far on this, we're going to go through synthetic division, but because it tells me this statement right here, negative 5 is a 0, I have to get a remainder of 0, non-negotiable, okay? If I don't get a remainder of 0, I have done something wrong because it already told me it's a 0. I have to get a remainder of 0. Negative 5 times negative 2 is 10, and boom, there it is, remainder of 0. Okay, we're in good shape. Hey, if I graph this one, and I'm going to put this into the calculator real quick here just to kind of show you this. To go about this. Last week when we talked about doing synthetic division, we started with a cubic polynomial. We broke it down by 1 degree, right? We've taken one of its zeros out. So this would now be 1x squared. And you could say plus 0x, but I don't really need to write 0x minus 2, right? So really I'm just going to say x squared minus 2. What we now have is we now have a quadratic equation that I still need to solve. Okay? And if I solved this, we can solve it using any of the methods that we did for solving quadratics. That would be things like the quadratic formula. Graphing it, we already graphed it. Graphing didn't really help us here because the decimals are my answers. Okay? But because it's missing a b value, it doesn't have an x in the middle, we could set this equal to 0. Not because we had a remainder of 0, just because it's a quadratic, and when we solve it, we always set it equal to 0. And we can do the square root method. That's going to be, by far and away, the easiest way to solve this one. Not always, but in this one, it would be. And we get plus or minus radical 2. Okay? And going back to what we talked about at the very beginning of the lesson, if I have a radical 0, it always has a conjugate, right? Positive radical 2 and negative radical 2. If I got one, I got another one, and that's because of the plus or minus in most scenarios, okay? So this one is a cubic polynomial. Negative 5 is 1 0, plus or minus radical 2 are my other two zeros. So it has 3 total zeros where it crosses the x-axis. Okay, let's look at another one that is kind of similar to this one. Okay, and once again, I'm going to give you, we're going to do one here in a second where I'm not going to give you a 0, but on this one, I'm going to say that negative 2 is a 0. Because they tell me it's a 0, we're going to go through synthetic division with negative 2. Okay, here's another place where you got to be really, really careful. Okay, when we did synthetic division last week, we said we're going to write our coefficients. But notice that this one is missing an x squared, right? It goes from 3 to 1. It doesn't have an x squared. So we have to put a placeholder in its place, a 0x squared. If you don't put that 0 in there, you won't get a remainder of 0, and you'll have a mistake. Okay, once again, because it told me a 0, I better get a remainder of 0, and sure enough, we do. We started with cubic. We're going to break it down by a degree. X squared minus 2x plus 1 is our leftover equation. And we're going to solve this. And there's a couple of different ways that I could solve this. I can't do the square root method on this one. I'm trying to show you some different scenarios of solving. Because there's a b value, we can't do the square root method. Probably the best method here would be to factor this, if we could, and we can. Okay? If you can't do any of those, then your go-to might be the quadratic formula, okay, which we're still going to see from time to time. But on this one, what would multiply to get 1 and add to get negative 2? Good. X minus 1 and x minus 1. Or we could write that as x minus 1 squared, which is really x equals 1. Okay, they're going to ask you sometimes, and this just is mainly because they want you to draw that conclusion between the zeros and the factors. So if I said, what are the factors of this polynomial and what are the zeros of this polynomial? First of all, we already know that negative 2 is a 0, and then x equals 1 is a 0, is what we just found. The factors are going to be x plus 2 and then x minus 1 squared. Here's another thing that we talked about last week. If I were to graph this one, okay, what's going to happen when I have a 2 as my exponent? It's what? It's going to bounce, right? Okay, it has a multiplicity of 2. So x equals 1 really counts as 2 zeros, okay? And you might say, well, how do I account for 3 zeros when I only actually have 2 of them? That's because 1 counts as a multiplicity of 2. It counts as 2 zeros because this is x minus 1 squared, which is x minus 1 and x minus 1. It happens twice, right? And that's why we say it has a multiplicity of 2, because it counts as 2 zeros. If we were to graph this one, let's just put this one in real quick. We're going to do a little bit of everything here. I'm going to give you a polynomial. It's going to be a little bit bigger polynomial than the last couple that we did. This one's going to be a quartic, or a degree 4. And it's essentially going to have 2 parts it's going to ask us to do. And some of the problems that we do today, this is what it's going to look like. Factor and solve. Factor means we want to write it as x plus 1, x minus 2, whatever the factors are. Solve means where does it cross the x-axis, or what are our 4 zeros that we have to account for. Somehow we have to account for 4 zeros. Okay, and so I'm going to write that down right here. We have 4 zeros that need to somehow be accounted for. This one is not giving us a 0 to start with, okay? So we could do the rational 0 theorem, but that's a lot of work and it really doesn't help us a lot. So here's where we can just jump right to our calculator, okay? Find at least one place where it crosses the x-axis. If I was going to give you a problem like this, I'm probably going to give you one that has, either I'm going to give you a 0 to start with, or I'm going to give you one where it crosses the x-axis at a nice whole number or integer, okay? So in this case here, we're going to graph first of all. So if we put this into our calculator, there. So x equals negative 1 and 1/3. There's 2 of our 4 zeros, okay? If you wanted to, you could go ahead and start writing your factors as well. This one would be x plus 1. This one would be x minus 1/3. Or if you wanted to, when we did like slide and divide, we wrote that as 3x minus 1. We took that 3 and slid it over in front of the x. I would be okay with either one of those. This would probably be the more correct way to write it rather than writing it as a fraction, but I'm okay with you just taking that 0 and writing it like that. Okay, so we got the first 2 zeros right from our graph. Now what we're going to do is we're going to go through synthetic division. Our goal here is to find the 2 imaginary zeros, but we have to have a way to get there, and this is how we're going to do it. Negative 1, we're going to put down our coefficients. Everything is accounted for. Because we already verified that it is a 0, we better get a remainder of 0. And we do. Okay, and then here's the trick. I don't have to go back to the beginning of the synthetic division. I can take what's left over as long as there's a remainder of 0 here. And I can now use the other 0 that we found, which was 1/3. 1/3 is our other 0. And I can do that. If you would rather move it down, you could move it down. I'm just going to leave everything where it's at. And now we're going to go through synthetic division a second time, using the second 0 that we had found. And this looks like it's going to be hard because, oh my gosh, we've got a fraction, right? But if I take 1/3 times 3, what do I get? Just get 1. Okay, 1/3 times 3 is just 1. -7 plus 1 is -6. If I take 1/3 times -6, it's really the same thing as taking -6 divided by 3. Okay, so it's not going to be that bad, right? -6 divided by 3 is -2. 8 plus -2 is 6. 6 divided by 3 is 2. And we get a remainder of 0. Okay, so here's what happens. We started with a 4th degree polynomial. The first time we go through synthetic division, we break this down to a cubic polynomial. When I break it down a second time, now it's a quadratic polynomial. So we went from 4th degree, then 3rd degree, to 2nd degree. Every time we go through synthetic division, our degree goes down by 1. Okay? So this would now be 3x squared minus 6x plus 6. We have to solve this quadratic equation. Can I factor it? Well, first of all, I can't do the square root method, right? That's out. Could I factor it? If I did, I would probably have to do slide and divide or take out a GCF. But we already said that our other two zeros are imaginary, and the only way to probably get there is quadratic formula. So that's where the quadratic formula is going to come into play. This is A, this is B, and this is C. So the opposite of -6 is +6. -6 squared would be 36 minus 4 times 3 times 6. All over 2 times 3. Four times 3 is 12. 12 times 6 is 72. 36 minus 72 would be -36. All over 6. What happens when we take the square root of -36? 6i. Both of these could then divide by 6. So we get 1 plus or minus I. And those would be our two imaginary solutions. Okay. Remember, they come in pairs, and that's where the plus or minus comes into play. 1 plus I and 1 minus I. Okay. If I go back up here, and I'm okay with you writing it as 1 plus or minus I. Okay. When I write the factors out, this is the part that gets a little bit weird. And one minus I and 1 plus I are my two zeros. So we always say x minus whatever that 0 is, kind of like when or my 0 is negative 1, I said x plus 1, but I have to take x minus the whole 0 and x minus this 0. And so if I were to rewrite this, it would be x minus 1 plus I and x minus 1 minus I. That's why I put it in parentheses there, because basically what we have to do is we have to take this minus sign and we got to distribute it through. And those would be my two zeros. Okay. I don't have a problem if you leave it like this, but the book is probably going to simplify it. So if you have an answer like this, then the book's probably going to simplify it to look like that. Okay. So lots of stuff goes into that one, right? We're using a lot of skills, synthetic division and quadratic formula and factoring and a lot of different things that we've used throughout the semester that are coming into play on something like this. All right, assignment for today. Okay, going by fives. Just pay attention to the directions today. What is it asking for? What are we trying to find? Each of the directions are a little bit different. We did a lot of different types of problems today.